Hi, my name is Becca Hahn, and I am a PhD student in geology at North Carolina State University. And today I'm going to be giving a quick overview of my research surrounding volcanoes on Venus. Venus is the second planet from the Sun. It's in between us and Mercury. And as you can see from this image taken by the Mariner 10, Venus has a very thick atmosphere and the surface is heavily obscured by thick clouds of sulfuric acid. So in order to penetrate that cloud layer to actually view the surface features on Venus, NASA launched the Magellan Orbiter, which was active between 1990 and 94, and used what's called synthetic aperture radar to penetrate that cloud cover and generate a nearly global map of the surface of Venus. So these radar images revealed a geologically complex surface of a planet dominated by volcanism, with volcanoes in a range of different sizes and even volcanic features that were completely unique to Venus. In order to better understand volcanism on Venus, I used the Magellan radar imagery to answer three main questions. The first question is, how are these volcanoes distributed across the surface of Venus? My second question is, how are these volcanoes shaped? How big are they? How small are they? Have any of them undergone a collapse or deformation event? And lastly, what can these volcanoes tell us about the underlying magmatic bodies and properties across the planet? In order to answer my research questions, I created a global catalog of shield volcanoes across Venus. I did this by using Esri's ArcMap to map 85,000 edifices across the surface of Venus. Here's my completed data set with major landforms labeled in purple. And as you can see from this map, these edifices are geographically widespread and cover virtually the entire planet. Using my global catalog, I was able to develop summary statistics for my shield volcanoes. So here I have divided my edifices into three groups based on their diameter, and those are shown in these first three columns. So my first group are edifices that are smaller than 5 kilometers in diameter. My second group are edifices that are between 5 and 100 kilometers in diameter. And my third group are shield volcanoes that are greater than 100 kilometers in diameter. And lastly, in this fourth column, I have deformed shield volcanoes. And these are volcanoes that have undergone gravitational deformation or some kind of sector collapse. So think of Mount St. Helens for reference. You might notice in this table that there is a shockingly high number of shield volcanoes that are smaller than 5 kilometers in diameter. In fact, this group makes up 98% of my catalog. So let's actually take a look at the dispersion of those edifices that are smaller than 5 kilometers in diameter. Here I have a density map or a heat map of those shields. And just from looking at this map, you might notice that there's a distinct decrease in spatial density of these edifices in the lowlands near the South Pole, and particularly in that southwestern quadrant. You might also notice these dark purple areas across the map, and these areas have a higher density of edifices and might indicate regions that have a readily available supply of magma to feed these smaller shield volcanoes. So what's next in my research? My next steps are to quantify the spatial dispersion of those smaller edifices by using statistical analysis to better understand the distribution and how they might give insight into the underlying magma bodies and magmatic properties. I'm also hoping to use a recently available stereo-derived topography dataset to actually calculate the volumes and heights of those edifices that are larger than 5 kilometers in diameter. But this is really dependent on the resolution and quality of the data. So thank you all so much for watching. If you have any questions, please feel free to contact me at rhahn@ncsu.edu.